So, as I said, my name is Gabi Nakibly. I will be presenting this talk on the routing table, which I will be presenting a new and powerful routing attack. The reason this attack is powerful because it exploits a vulnerability which actually lies within the standard of the OSPF routing protocol. Now OSPF is one of the common routing protocols around, and since the vulnerability lies within the standard of the protocol, as you will shortly see, many router vendors are indeed affected by this vulnerability. This is actually a second part of our work or our research on OSPF security. The first part we presented here at Blackhat 2 years ago, and now we push the envelope even further and present an even more powerful and simpler attack. Actually, it's so simple, as you will shortly see, that an attacker can DOS a Cisco router using just a single packet. This is a joint work with Eitan Menachem, Ariel Weisel, and Yuval Elovich from Ben-Gurion University. Okay, just a quick introduction about myself before we start. As I said, my name is Gabi. I'm a fellow at the National Lab in Israel called the National Electronic Warfare Research and Simulation Center. We provide high-end research and consulting services. I myself am involved in network security. I'm also an academic researcher and lecturer at the Technion in Israel, where I teach and research network security. Okay, so let me give you just a brief overview of what you're about to hear today. The target of many routing attacks is actually control or alter or poison in some way the routing tables of a remote router without actually having to go through the trouble of actually owning the router itself. The attack I'm going to present today does just that. As I said, it is presented on it is based on a newly found vulnerability of the OSPF protocol, and it actually allows to own the routing table of other routers within the routing domain while using just a single compromised routing within that domain. Routing domain can be, for example, an ISP network, an enterprise network, and this means that an attacker only needs to compromise just a single router within that domain in order to compromise all the other routing tables within that domain. So why is this so desirable to compromise or own the routing tables of other routers? If you own the routing table of another router, you actually can control the path a packet takes through the network. And if you can do that, you actually can do many nice tricks with it. For example, you can induce black holes, create network cuts, simply partition the network. You can do traffic diversion, make the packet go through longer routes in order to facilitate eavesdropping or increase the load on the network, and so on and so on. So who is vulnerable to the attack? Now, as I mentioned, the attack exploits a vulnerability embedded in the OSPF standard, actually in RFC 2328. So this means that potentially many commercial vendors may be vulnerable to this attack. And indeed, currently now, we know of several router vendors which are affected. Here are they in alphabetical order. Actually, this talk is a culmination of a multi-vendor effort to patch this vulnerability, and I would like to thank the CERT-CC for their coordination of this effort. Actually, I haven't personally verified all of the attack on all of these router vendors, but I will focus on the second half of my talk on perhaps the most interesting vendor here, which is of course Cisco. So this is the agenda of the talk. First, I will walk you through some of the fundamentals of OSPF and how it works. Then I will describe some of the OSPF security strengths, and then of course the newly found vulnerability and attack, and as I said, then the attack's effects on Cisco router. Okay, so let's start with the big picture, internet routing and how it works. So probably as many of you already know, the networks and routers of the internet are actually clustered into groups which are called autonomous systems. Each autonomous system is administered by a single network operator or maybe a few network operators. There are some, I think, 45,000 autonomous systems on the internet today. So this means that actually the routing on the internet works in two levels. The higher level is the inter-autonomous system routing, which means that the autonomous systems through which the packet traverses is determined. This is done using the BGP protocol. Okay, and at the lower level, there is the routing within each autonomous system, which of course determines the path the packet will take through each autonomous system. Now, this is done independently within each autonomous system, and each network operator is free to choose which routing protocol to do this routing within the autonomous system. The most popular choices are OSPF, RIP, and ISIS. And as I said, I will be talking about OSPF for this talk. Okay, so let's review some of the OSPF fundamentals. So how OSPF works? OSPF works by having each router advertise a link state, meaning that each router advertises who are its immediate neighbors, to whom it is connected directly to. This advertisement is called the link state advertisement, or LSA for short. And the LSAs are actually flooded throughout the autonomous system, hop by hop, meaning that each router advertises its LSA to all its immediate neighbors, they advertise it to all their immediate neighbors, and so on and so forth, until all the routers receives this LSA. This means that each and every LSA, each and every router receives all the other LSA's routers. And now every router can actually compile its view of the autonomous system topology. Based on this view, the router can calculate its routing table. Now let's see an illustration of how it works. Let's say this is our autonomous system. We have a bunch of routers and networks connected to each other. Now let's assume now that R1 advertises its LSA, which of course is distributed or flooded throughout the autonomous system. Now every router which receives the LSA keeps it in a special data structure called the LSA database, or LSADB. And now every router knows that R1 in this example is connected on one interface to this local area network and on the other interface to R2. When R2 advertises its LSA, then it is of course again flooded throughout the autonomous system, and now everybody knows that R2 is connected on one interface to R1 and on the other two interfaces to these two other routers, and so on and so forth. And this is how each and every router composes its view of the autonomous system topology. And as I said, based on this view, the routing table is calculated. Now, for simplicity reasons, I don't mention here the notion of areas. I assume here that the autonomous system here is composed of just a single area. Okay, a few more details about an LSA. LSA is advertised periodically, by default every half an hour. Every LSA has a sequence number, which is incremented sequentially with every new advertised instance. This means that newer instances of an LSA with higher sequence number will always take precedence over older instances of the same LSA with lower sequence number. And in addition, there are several types of LSAs. The most important one is router LSA, which actually describes the links of a router. There are several other types of LSA, for example, network LSA, which describes the links of a given network, but I will not consider them for this talk. Throughout this talk, when I say an LSA, I mean router LSA. Okay, and now for the attacker. In our research, we have assumed that the attacker is an insider, meaning that it has been able to infiltrate the routing domain, the autonomous system, and is now controlling just a single router within the autonomous system with an arbitrary location. It can be not necessarily be a core router, it can be just a remote access router somewhere in the autonomous system. Now, we needed to assume this because we wanted to search for OSPF attacks. In order to search for OSPF attacks, the attacker needs to send OSPF messages to at least one other router within the autonomous system. Now, there are cases where the attacker can do it from the outside. In such cases, then the attacker doesn't need to take control over the router within the autonomous system. And the goal of the attacker is to significantly control the routing tables of the other routers within the autonomous system. Okay, it controls just a single router, and now he wishes to control the routing tables of all the other routers. Now, let me just recap for you some of the OSPF security strength and why it has been so hard or even impossible in the general case for an attacker to achieve such a goal. So here's an example. Let's say we have this autonomous system and we have an attacker that managed to take control of one of the routers up there. And he now wishes to poison some of the routing tables of some of the routers within the autonomous system. Specifically, we will be focusing on the router there on the right, which the attacker now wishes to poison its LSA database. The router now has a complete and correct view of the autonomous system topology. And let's say that the attacker now wishes to poison the routing table or poison the LSA database of this router by disconnecting the victim router down there. So that the poisoned router will not be able to route to this victim router. Let's say it serves some purpose for the attacker. Now, the most simple way the attacker can achieve this is by simply sending out a false LSA on behalf of the attacker, on behalf of the victim, saying that the victim has no links whatsoever and is not connected to any other router within the autonomous system. This will achieve the goal of the attacker. Now, the first security strength is that every LSA is flooded throughout the autonomous system. This already you know. This means that once the attacker floods or advertises the LSA, the false LSA on behalf of the victim, it will simply be flooded throughout the autonomous system. As of itself, this is not a security strength, but it does mean that eventually the victim will receive the false LSA advertised on its behalf. Now, this poses a problem for the attacker because of the second security strength, which means that, which is the fightback mechanism. The fightback mechanism is defined in the OSPF standard, and it says that once a router receives a false LSA advertised on its behalf, the victim router will immediately send out a correct LSA with a higher sequence number. And this is the fightback LSA, which of course will cancel out the false LSA because it has a higher sequence number. This is the fightback. So in this example, the victim router will immediately send out the fightback LSA, and this will revert the attack's effect. The attack will have a non-persistent effect on the LSA databases of all the other routers. Okay, so another attack venue the attacker might wishes to take is to simply send out the advertisement, the false advertisement directly to the router wishes to poison. This is done using simply by unicasting the packet directly to that router. Now here comes another security strength of OSPF, which is LSA authentication, which means that every link in the autonomous system is associated with a secret, which is shared among all the routers, all the directly attached router, directly attached to this link. And these routers use this use this secret in order to authenticate the LSAs they share or they exchange among themselves. In our example, the attacker knows the secrets of all the links that are directly attached to it. In this example, secret X, but he doesn't know the other secrets. For example, secret Y. So this means that the router to be poisoned will not be able to authenticate the false LSA advertised by the attacker, and it will simply be discarded. Okay, and actually this means that an attacker is not able to poison or persistently poison in a general case the LSA database of one router by falsifying an LSA of another router, of a third router, okay? Because once he does that, the third router, the other router will simply fight back, making the attack's effect non-persistent, okay? So the common conception is that an attacker, even if it is an insider, he simply cannot significantly and persistently poison the routing table of a router he does not control. Excuse me. Now this has been the conception indeed up until 2011. This is when we published our first part of our research, and then we presented the first general technique to evade fightback, and thereby persistently falsifying LSAs advertised on behalf of some other router. We call this technique disguised LSA. You're welcome to check it out on the web. And this technique also relies on a vulnerability embedded in the OSPF standard. Now, in the new attack, we also affords the ability to persistently falsify LSAs on behalf of some other router. It also exploits a vulnerability which is embedded in the OSPF standard. However, it does offer some added advantages, which is first, it offers full poisoning, meaning that we can now, using the new technique, new attack I'm going to present, we can poison 100% of the routers within the autonomous system, and this is including the victim itself, meaning the victim itself will now believe the false LSA we will be advertising on its behalf. And the previous attack only poisoned just some of the routers within the autonomous system, certainly not the victims. And the other one is that it's simplicity. As you will shortly see, the attack is dead simple. It's embarrassingly simple. And it only requires just a single packet, the actual false LSA the attacker will advertise. Okay. So finally, let's dive into the details. And here's a snapshot of the LSA header, which I've taken directly from the RFC. And here you can see all the fields in the LSA header. We have here the age of the LSA, which is simply the number of seconds elapsed since its origination. We have some options, and then the LSA type. As I mentioned, we will be considering an LSA of one type, which is the router LSA. And then these two fields, link state ID and advertising router, which I will be discussing shortly. And then the sequence number, which I've already mentioned. And then the checksum of the LSA and the length of the LSA. Now, in section 12.1 in the RFC, it says that an LSA is uniquely identified by these two fields, advertising router and link state ID. Actually, I'm bluffing here a little. The RFC says that an LSA is identified by three fields, these two and the LSA type. Now, since we are considering only router LSAs, I will just ignore the LSA type for simplicity reasons. So, from our point of view, an LSA is identified by these two fields, advertising router and link state ID. Let's see what they are. A link state ID actually identifies the part of the autonomous system that is being described by the LSA. In the case of a router LSA, since the LSA describes the links of a given router, then the link state ID would be the ID of that router. The ID of the router is simply an IP address of one of its interfaces. And the advertising router field identifies the router that originated the LSA. Now, since the LSA of a given router is always originated by that LSA, by that router itself, no other router will ever originate LSA on behalf of some other router. So this field should also be the ID of the router. Now this means that both fields, these two fields, should have the same exact value, the identity of the router of that LSA. Simple enough. However, interestingly enough, the OSPF specification does not specify a check to verify this on LSA reception. Once a router receives this LSA, there is no sanity check that verifies that indeed these two fields are the same. So let's see what kind of interesting stuff a router an attacker might be able to do with this piece of information. So this is the basic vulnerability which the attack relies on, at least the first part of the vulnerability. So according to the OSPF specification, section 13.4, a router fights back only if it receives a false LSA in which the advertising router is equal to the router's own router ID, meaning that once a router receives a false LSA, it will fight back only if the advertising router field in that LSA equals to its own ID, its own router ID, regardless of the value of the link state ID. This means that actually if an attacker sends out a false LSA with the following header, then there will no fightback will be triggered, meaning that if the header contains a link state ID that does equal to the victim's router ID, but the advertising router does not equal to the victim's router ID, then no fightback will be triggered whatsoever. And this is despite the fact that this LSA claims to describe the very links of that victim router. No fightback will be triggered. So actually the basic attack works as follows. Let's assume that the attacker is up there and he now wishes to send out a false LSA on behalf of some of the victim in the middle there. So it will just simply send out a false LSA with the LSA header we just seen. And the LSA will just be flooded throughout the autonomous system. All routers will actually install the false LSA in their database. This includes now the victim, and now no fightback will be triggered. Actually, again, the victim will actually install the false LSA in its own database. The LSA will actually advertise on its behalf, and moreover, it will continue to flood this LSA to all of its neighbors. And this is how we get 100% poisoning of all the autonomous system. Now, it's simple enough. However, it's not that simple. We have a problem here. Remember section 12.1 of the RFC? An LSA is identified by both fields, link state ID and advertising router. This means that the false LSA we just advertised has a different identifier than the valid LSA, the actual correct LSA of the victim router. So, because they differ in the advertising field. So, indeed, the attacker managed to send out a false LSA, and we did manage to avoid the fight back, but it seems that the attack is futile because actually we have managed to falsify an LSA that does not really belong to the victim because they have different identifiers. Okay, and this is what I just said. And now for the second part of the vulnerability, which is actually an ambiguity in the OSPF specification. In section 16.1, according to the standard, during the routing table calculation, when an LSA, when the router fetches or looks up LSA in its own LSA databases, an LSA is looked up based on the vertex ID only. In this context, by the vertex ID, the RFC means the link state ID. So we actually have here a bit of an ambiguity. In the general case, on section 12.1, the RFC said that actually the LSA is identified by both fields, link state ID and advertising router. However, as you can see here on section 16.1, during the routing table calculation, the LSA is identified only by the link state ID during its lookup in the LSA database. So we have an ambiguity here. And actually, if we just now step back a minute and review what we have after the attack, then we have, after the attacker advertised or flooded the false LSA on behalf of the victim, we have in every router two LSAs having the same exact link state ID, the false LSA and the valid LSA. They have both the same exact link state ID, which is equals to the victim's own router ID. So this gives rise to the following question. During the routing table calculation, when the LSA of the victim router is fetched, which LSA will be fetched? The false LSA or the valid LSA? Of course, if the false LSA will be fetched, then we are home free. If the valid LSA will be fetched, so actually the whole attack is futile. Of course, now the RFC does not give us an answer to this question. So the answer is undefined as far as the standard is concerned. So this is actually an implementation dependent answer. Every implementation might fetch the false LSA or the valid LSA. Now, as you have seen at the beginning, indeed many commercial routers indeed fetch the false LSA, making the the attack successful. And indeed, we'll now be talking about the case of the Cisco router, and let's see how the effects went on a Cisco router. So in order to validate the attack, we use the GNS3 emulation software, which is a software which can emulate Cisco's iOS real production image, which is supposed to be run on a router on a PC. We use the Cisco's iOS 15.01m, which is almost the latest iOS version, and we use the SCAPI to craft the attack packet. Okay, so this is our first finding. Once we have advertised a false LSA on behalf of the victim router, using a higher sequence number than the sequence number of the valid LSA, then not only that the false LSA was indeed installed in the routers, in the LSA database of all the routers, but it actually replaced the valid LSA of the victim router. And this happens in all the routers, including the victim itself, meaning the victim itself erases its own LSA from its own LSA database, and it now replaces it with the false LSA we advertised on its behalf, which was quite interesting. Here is an example of a snapshot of an LSA database from our experiments. So here you can see the LSA database of the victim router. Here you have the ID is 37.3, and here you can see the valid LSA, which has a link state ID of 37.3 and advertising router of 37.3 as it should. This is before the attack. And after the attack, again, the link state ID of 37.3. And here you can see the false LSA, which have a link state ID of 37.3 and an advertising router of 27.11. This is some kind of an arbitrary number I've chosen. And indeed, the LSA database after the attack does not include the valid LSA. It was simply replaced. Okay, so indeed, all the routers consider the false LSA during the routing table calculation. Actually, they have no choice because the valid LSA is erased. And indeed, all the routers except the victim itself calculate the new routes in accordance with the new information in the false LSA, except the victim. The victim had a much more interesting behavior. The victims actually erased all its routing table. At first glance, it seemed like he just committed suicide following the attack. But actually, after we looked at it, we saw that indeed the victim router also takes into consideration during its routing table calculation the false, of course, the false LSA. It doesn't have the valid LSA. And it does calculate the routes correctly, but somehow it does not install the routes in its routing table. This means that all the OSPF routes are now erased from the routing table, and this means that all the routes that are based on OSPF routes, for example, some BGP routes, are also erased from the table. So actually, this leaves the victim router with almost empty routing table, which makes it, of course, a useless router with an empty, a router with an empty routing table. It's actually useless. So, and we find out that this erasure actually was quite persistent. The victims could not simply recover from this erasure spontaneously. The only way the victim could recover is by simply either rebooting the router or reloading the router, or by simply just erasing the OSPF configuration and then enable it once again. So this was a very persistent erasure of the routing table, and now the nice trick about it is that the attacker itself can now can actually undo this erasure and actually undo the entire attack effect by simply just sending another false LSA but this time with the correct advertising router ID. And then it will just trigger a fightback by the victim router with a higher sequence number. And then this will cancel out the false LSA we sent out previously, and everything will be back to normal. So this is actually a nice feature of this attack, where the attacker can just, like a on and off switch, can actually make the attack go away. Okay, so this was the validation of the Cisco router. Now to recap, just let me give you two examples, two application examples of the attack. One example is black hole. Let's say the attacker wishes now to create a black hole within the autonomous system for a specific external destination. So it can, for example, send out a false LSA on behalf of the victim router, saying that the victim router now is directly connected to some external destination, for example, the IP range of google.com. And this will eventually make all the packets in the autonomous system will be rerouted to the victim itself. And now, since the victim actually has no routing table, of course it will become a black hole. Another example is traffic diversion. Simply by changing the routes of the packet tag. For example, in this scenario, we have the green path, and let's say the attacker wishes to change it, and so that the new route will pass through it. So in this particular scenario, what the attacker can do is just send a false LSA on behalf of the victim router, saying that the victim router is now disconnected from the network. It has no links whatsoever. So it will just simply advertise it, and in this scenario, the new route will actually traverse the attacker, and now the attacker can eavesdrop on the traffic or launch man-in-the-middle attack. Okay, and this was just a couple of attacks on attack examples. Okay, so to conclude, actually what I've presented here is a new attack on OSPF routing protocol. Using this attack, if the attacker can compromise just a single router within the autonomous system, it actually can compromise all the routing tables within that autonomous system. And the main takeaway I want you to take from this talk is that the integrity of your routing domain depends on the security of the least secure router within your domain. This means that you need to secure your remote access router in the remote branch as much as you secure your core router in your main branch. So this was my talk. I will be happy to answer any questions you might have. Yes.
If you craft a packet and send it out from a host on a segment that was listening to OSPF, could you do it without controlling the router?
Well, you would need the secret of the link. There is the LSA authentication. Okay. Yes. Excuse me? I'm sorry, I'm having trouble. There is no OSPF authentication anymore?
Can you do an arbitrary packet if there is no OSPF authentication?
Okay. If there is no OSPF authentication, then actually you can actually probably do this attack from actually outside the autonomous system, maybe even send it remotely. Then you're in deep trouble. Yeah.
Is there a legitimate reason to set an LSA with a link ID
No. No, there is no reason for that. Actually, Juniper and Cisco, I think, patched this vulnerability by actually looking for this kind of LSAs. Okay, they actually did a sanity check to verify that indeed the link state ID is equal to the advertising router. No, there is a very distinct reason why they were in here, because of there are other types of LSA in which these two fields are not the same. For a router LSA, these two fields must be the same. For other types of LSA, they not necessarily be the same. Okay, so thank you very much. So, as I said, my name is Gabi Nakibly. I will be presenting this talk owning the routing table, which I will be presenting a new and powerful routing attack. The reason this attack is powerful because it exploits a vulnerability which actually lies within the standard of the OSPF routing protocol. Now, OSPF is one of the common routing protocols around. And since the vulnerability lies within the standard of the protocol, as you will shortly see, many router vendors are indeed affected by this vulnerability. This is actually a second part of our work or our research on OSPF security. The first part we presented here at Blackhat 2 years ago. And in order to facilitate eavesdropping or increase the load on the network and so on and so on. So who is vulnerable to the attack? Now, as I mentioned, the attack exploits a vulnerability embedded in the OSPF standard, actually in RFC 2328. So this means that potentially many commercial vendors may be vulnerable to this attack. And indeed, currently now, we know of several router vendors which are affected. Here are they in alphabetical order. Actually, this talk is a culmination of a multi-vendor effort to patch this vulnerability, and I would like to thank the CERT-CC for their coordination of this effort. Actually, I haven't personally verified all of now we push the envelope even further and present an even more powerful and simpler attack. Actually, it's so simple, as you will shortly see, that an attacker can DOS a Cisco router using just a single packet. This is a joint work with Eitan Menachem, Ariel Weisel, and Yuval Elovich from Ben-Gurion University. Okay, just a quick introduction about myself before we start. As I said, my name is Gabi. I'm a fellow at the National Lab in Israel called the National Electronic Warfare Research and Simulation Center. We provide high-end research and consulting services. I myself am involved in network security. I'm also an academic researcher and lecturer at the Technion in Israel, where I teach and research network security. Okay, so let me give you just a brief overview of what you're about to hear today. The target of many routing attacks is actually control or alter or poison in some way the routing tables of a remote router without actually having to go through the trouble of actually owning the router itself. The attack I'm going to present today does just that. As I said, it is presented on it is based on a newly found vulnerability of the OSPF protocol, and it actually allows to own the routing table of other routers within the routing domain while using just a single compromised routing within that domain. Routing domain can be, for example, an ISP network, an enterprise network. And this means that an attacker only needs to compromise just a single router within that domain in order to compromise all the other routing tables within that domain. So why is this so desirable to compromise or own the routing tables of other routers? If you own the routing table of another router, you actually can control the path a packet takes through the network. And if you can do that, you actually can do many nice tricks with it. For example, you can induce black holes, create network cuts, simply partition the network. You can do traffic diversion, make the packet go through longer routes.